Good evening, everyone. It's Jenly Chu here from the RCEA, or from the event venue. So Dr. Christopher Nicholas has arrived on site, and we will begin the presentation momentarily. So good evening, everyone. I'm Jenly Chu. I'm here hosting this event on behalf of the Railway Civil Engineers Association. So welcome to today's evening seminar. I am Jenly Chu. I'm chair of the Railway Civil Engineers Association. In my day job, I'm engineering manager and formerly temporary works coordinator at the Colindale Station project for Morgan Sindall. And I also work on behalf of Morgan Sindall Engineering Solutions as a temporary works design engineer. For all involved, so you know, we will be recording this event and it will be made available on our RCEA YouTube channel afterwards. We will be sending out the link to the recording on a newsletter to everyone who's registered for this event, and it will also be shown on our website as well as our LinkedIn page. What happened there? So to briefly introduce you, today's talk is about Coventry Very Light Rail, presented by Dr. Christopher Nicholas, in which the Coventry Very Light project is going to be reimagining urban transport with a novel shallow track form and smaller autonomous railway vehicles to lower the cost of construction and maintenance and operations, and therefore make public transport more affordable and feasible going forward. And so this lecture will explore the design, testing, and future impact on UK transport infrastructure. So to quickly introduce the RCEA, we were founded in 1921 to encourage exchange of knowledge and experience between railway civil engineers. In 1997, we became part of the Institution of Civil Engineers as a specialist society. We currently have over 470 members, and then we do a series of events throughout the year, normally evening seminars about 10 times a year on the last Thursday of the month. And last year, we also did some lunch and learns, which we are also going to be exploring doing this year as well. In order to find us on the ICE website, you can find us under Specialist Knowledge Societies. You can Google us, RCEA or Railway Civil Engineers Association. Go to our website, and yes. So for information, if you are interested in becoming a member of the RCEA, this is our list of membership fees for ordinary members, young professionals, students, and retired members. We've raised our fees modestly this year from last year after having kept our fees frozen since the year 2020. Which I think very few people can say that they've done so. And if you're interested in getting involved, our next committee meeting is next Tuesday, the 27th of January at 5 p.m., held for 1 hour online. And if you're interested, please email rcea@ice.org.uk for more details. And finally, before we start the presentation, this is a page of our future events, where on the 26th of February, we have a presentation by one of our members, Tim Kendall, retired chartered civil engineer, on how he believes that Dr. Beeching saved the UK railways in the 60s. And he will go through the context for why Beeching's acts was performed, what actually was in the report, and what is the future of the British Railways going forward under Great British Railways. On the 26th, that will be held in person in London at the ICHQ and online. On the 26th of March, we will have an online-only presentation on the Mid-Cornwall Metro project, which is to upgrade the railways from Par to Newquay and allow for a through service from Newquay to Par to Truro to Falmouth. And then on the 23rd of April, we will be having our annual conference in AGM in 1 Great George Street. We are currently actively involved in planning and organizing the event, and it promises to be a very exciting one. And without further ado, we shall introduce Dr. Christopher Nicholas on the Coventry Very Light Rail. Good evening, Chris.
Good evening. Thank you, Jean. And thank you, everybody, for your kindness and waiting. I guess first lesson of today, when you tend to be an optimist, and then something happens out of your control, you'll always be late, right? So Okay, so
I'll do it. I'll click it. Yeah.
So today we're going to cover quite a lot. I was thinking about what to focus on: too technical, program management, reality of the world we live in. So it's going to be a mix of everything, because in reality you can't really separate any of these elements from each other. There's going to be a history lesson of this CVLR. It's a very abnormal project in a lot of ways. I wish to give you a flavor of everything that we've been doing. I'm going to start with the introduction on the concept. Why does it even exist as a program? Then the two sections following that are a bit more technical. The first one look at the specification of this track we've been developing. And the last section is really how do we build evidence around this new track? The reality is a lot of track goes around the UK. A lot of it, if you go and start asking deep questions, people will answer you because we've always done it like that way. Or that's the spec I was given and put it in the ground. But as soon as you start proposing something novel, then all of a sudden everybody's an expert. And that's fine and that's fair. The onus is on us in proving and demonstrating that what we've been building actually is robust enough. And that's what I'll give you a bit an idea of. Oh, trams. Trams, believe it or not, is what probably what created modern cities. It is what used to move people around in cities. And the UK really was at the heart of this innovation. I mean, cities wouldn't have come to exist with their nature if we weren't able to move people efficiently around. And as you see, that's what's landing. Trams were at the heart of public transit, right? Cities were never designed for cars, and that's part of the problem we have today. Excellent. No, I think I prefer to do it.
Okay. Okay. Yeah.
So what is the situation that we find ourselves today, right? So light rail, as you would see there, and Germany, because it's actually retained most of its systems, has about 60 networks left around the country, right? France have been building aggressively. They've got about 30 networks. The UK, depending which ones you count as light rail, up to 9 systems left. And unless something changes, we've just seen before Christmas, Leeds, the biggest city in Europe without a light rail system, is probably looking at years and years and years before they will get one. Right? And we'll look at the reasons of why this situation is. Just to give you an idea, right? If we look at Germany, those 60 networks, they removed about 4 billion passenger journeys in 2024. That's 11 million people that travel on such a transit. And so, yes, it's a summary of the last one. The UK is really way behind other European countries and cities in terms of its light rail adaptation. There's no other way of looking at it. Coventry. Coventry had trams, as you might be aware of, as did most of other UK cities, but it lost them, partly because of the war, but more than the war, and I'm not speaking just specifically about Coventry. Most other tram networks were abandoned purposefully, and it's not because the people didn't want them. The last tram to close up in Glasgow, there were about 250,000 people in the streets celebrating the last tram journeys. So people always loved these modes of transit, and they still do. They are one of the most effective ways of creating real sustainable cities. And that's why Coventry has this vision of bringing back a full light rail network around the city, right? And that's what you see down there is our aspiration. That's what we want to try to achieve, deliver a full network of light rail around the city. And why are we trying to achieve this? I mean, we strongly believe, and this is backed by science and evidence, that a light rail implementation in a city can really bring significant advantages to a city. When delivered in the right way, it's been proven over and over that it can really drive economic regeneration. The government invests X, private industry brings multiple factors of that. We've seen over and over that wherever light rail gets implemented, property around it increases in value more than anywhere else in that city. In terms of performance, nothing comes close. It's zero and local emissions and real zero emissions. I mean, nothing is zero emissions, but compared to a bus, it doesn't suffer from the tire emissions, right? It is, of course, you're putting a lot of people on one single vehicle. By its definition, it is sustainable. And the final aspect is when designed right, trams can really transform city centers and transport corridors because they are gentle vehicles. They are repeatable. You always know where a tram is. Seeing a tram come your way isn't like seeing a bus or a lorry coming your way. The certainty of steel on steel gives you the confidence that you always know where that vehicle is. That's why you see people walking in front of trams in cities, because that repeatability of motion of trams and that smoothness gives people this confidence in being able to live very close to them. So that's the vision, right? What has Coventry been up to? So Coventry has set up this project, and it's been quite a unique collaboration, if you'd ask me, where it has really been a successful collaboration where government, academia, and this industry have come together in a real collaborative fashion. I put that figure there, 30 million. It's expired. We've created more than 50 million pounds of research in this project, including this last phase. And it must be said that funding is not Coventry's council tax. It's all R&D funding that we have been able to achieve step by step, very painfully, but it's reality. And this is by no means an exhaustive list of partners. I myself was one of the lead researchers at WMG to start with, and since then I've moved working directly at the Coventry City Council. Cola Sanger, Moss Atkins have been a few of our key partners, but in reality, and particularly on the track project, this program would have never existed if it weren't for so much collaborative and a lot of in-kind help that I've got from more than 50 companies that have supported and believe in this program. Okay, so back to the why is this program needed? Why is Coventry? Why has Coventry embarked on this R&D project, right? So what you have here on the screen is a bit of a snapshot of what we're dealing with. This is not a scientific comparison of costs of light rail. You can never compare a project with another, right? And that's not the aim of this slide. But these numbers are maybe even more important than a scientific comparison of costs. This is what people know, and this is what politicians know. And these numbers are extremely scary. No politician will not come close to these numbers because they are seen as excessive. And actually, the details behind them can make these projects even scarier than what they look like. And then there's another aspect to it. In the UK, there is this very aggressive push by the government and belief that they want these projects, these public transit projects, where most of them in Europe are delivered to deliver for the benefit of the people. So they are public investments for the people. In our case, we want these projects to be self-sustainable in terms of the investment, right? We want them to have really solid business cases. And if anybody of you has been involved in these business cases, they are quite perverse in the way they are set up. Just to give you an idea, right? If I'm building a business case for this light rail, and we're intentionally diverting traffic because we want to give priority to a more sustainable mode of transit, in my business case, I need to account for the delays I'm causing the traffic I'm intentionally diverting. And that's just one example, right? On the other hand, we never account in the business case for the damage that private cars or so on actually cause on us, right? So it's a real fake business case because it doesn't account for all of these real factors, right? Nobody accounts for how many people we send to the NHS because of pollution, right? So that's why this business case is a fallacy in the end, right? But without these business cases, these projects cannot exist because you're never gonna get funding for such projects. So that's the reality we live in, right? Coventry City Council had been doing a lot of studies looking at what could make sense. And this is a number, and probably it was an aspirational challenge that they've given us as researchers at the university. They told us we could put together a business case for this early rough route that we have in mind. But it could only actually work if we have something that costs 10 million a kilometer. And so there you could see the challenge that we had on our hands, right? And that's what we started working on. Basically, a blank sheet of paper and this challenge set to us as researchers by a local council who just didn't want to give up. They wanted to see if something could be done, right? They wanted to see if we can come up with an answer. And that's where I started with, right? Because I didn't want to waste a single day of my life if I didn't need to. The first thing I started looking, is this completely delusional, right? So I started asking, how much does a steel rail cost? How much does concrete cost, right? How much does asphalt cost? Why on earth are we spending 70 million a kilometer, right? Does track actually cost 70 million a kilometers? What's the cost of a tram, right? Okay, a tram is 2 million, 3 million, right? So why on earth are we costing these hundreds of millions on a project? So that's where it started. And I guess the realization I came to is that track really is neither slow or neither that expensive. And by that I mean, right? You could probably build high-speed rail track at about 3-4 million a kilometer. That's the actual cost of track, right? Of the final what we call the superstructure. Yeah. And in terms of speeds that you can achieve, you can look up that. This is was one of the biggest European-wide research in rail. Those are rates that you could achieve. So 100, 500 meters a day. But we all know that we close city centers for years when we are delivering train, right? So what's happening, right? And I think you've already figured it out, that it's not the track infrastructure, which is the challenge, right? It is all of the enabling works that are necessary to put track into the real world. It's very obvious, right? Until you start looking at the numbers. And then essentially all I'm saying is that this gives the foundation to our project. And then you start looking at the real world. This is in ChatGPT. It's a photo I took myself, and that is Edinburgh. And before the tram in Edinburgh could actually go on its way, everything you see there had to be moved out from where it is. And to make things even more interesting, every single color means they belong to a different privately owned company, which means they have the right to make us pay for that move. And that's part of the challenge. So we started to put some numbers around that. Manchester Metrolink, 400 separate utility assets had to be moved for just 1.3 kilometer route. Those are 400 projects, right? All with their own complexity and costs and challenges. Plus, they are all interfacing with each other. If we look at Edinburgh, yeah, you all know about the problems that there were. I mean, Edinburgh was approved by Parliament at about 350 million. It ended up costing more than $1 billion, right? For half of the scope, half of the route. And most of that was because of the complexity they met when they started digging and dealing with utilities. In Birmingham, 16 million a kilometer, in that last section was just cost on utility diversions. And that's actually net. It's not real, the actual full cost related to utility diversions and other enabling works. The number is even bigger than that. And so this is what CVLR is all about. It is a journey. It is an R&D project to try to look at things differently. The industry is completely focused on subcomponents most of the time, right? The industry is completely fragmented and very, very niche in a lot of areas, right? So there's a few sleeper manufacturers. There's a few fastener manufacturers, right? There's a few engineering consultancies putting these together. Nobody actually has the holistic control or ownership of a full track system. Very, very few parties exist with that nature. And if you would decide as a private entity to embark on a journey of developing a whole new system on your own, well, not a lot of people have done that and succeeded. There's a lot of projects, R&D projects, which stay there. So CVLR set on not dealing with coming up with something which is better than what exists. We are never going to be better than somebody who has been doing something for 100 years, right? They're experts in that field. But the aim of CVLR was to look at the real costs behind these light rail projects. The costs are coming from earthworks, from utilities, and the complexity that these bring about, the massive project durations which we deal with. So CVLR track was designed from the ground up to try to give us a system which deals with the costs in that area there. Does that make sense? So to go into a bit more detail on how we set about trying to achieve this, right? This vision, and then start going from vision to engineering, right? We essentially set up these targets for ourselves. We did set a full program about coming up with a new vehicle, and I'm just going to touch 2-3 slides on that today. The vehicle is a key enabler, and also we have to keep in mind that a lot of these decisions were taken in 2016, 2017, right? The world is a very different place. And in a lot of ways, actually, the market is following our vision from back then. So some things are becoming easier than they were before, because battery technology, for example, is so much better than it was in 2017. So the tram itself, it's a key enabler. As I'll explain, two of the main advantages that we sought to extract from the vehicle are mostly because it's onboard energy, right? If the vehicle doesn't, if I don't, as the infrastructure engineer, I don't need to provide energy to the tram via the typical catenary, right? Then, of course, the simplifications are very obvious. We don't have to build all of the overhead catenary. And also, for us track engineers, we do not have to deal with stray currents, which is a massive issue with typical light rail. And I'll show a bit more than that. Time, personally, I think it's probably one of the biggest aspects in all of these projects. These projects are taking way too long. We're talking about probably 10, 15, 20 years as the minimum timeline you have to keep in mind. If we're talking a city that a mayor decides, I want to have light rail in the city, if anybody tells you it's going to take less than 15, 20 years, they're delusional. And the reason for that is the layers of procurement and systems and resource availability that we have, and the way we're doing things. We want to try to modularize the design, simplify the design, accelerate the design process, and then delivery of these projects, that we really try to compress that process. It needs to really become a 5-year project. And 5 years is quite critical, because if these projects do not fit within political cycles, then they can really never exist in the future, because very few politicians have the courage to start on a process, absorb and eat all of the pain, only for somebody else to cut the ribbon 15 years down the line. And that is a massive, massive challenge we have on our hand. So these projects must be compressed to a timeline that somebody can say, I'm going to go for this, and in 5 years, I'm going to be showing results to the people so that I get re-elected. And as you see, these factors, they're not really engineering, but I've learned over these last years that these things are actually much more challenging to deal with than the engineering. The engineering has been very simple in this project, and I'll show you very soon what I mean by that. The other aspect is the track construction in itself. Some problems nobody can solve. The unknown is the unknown. And so one of the mantras of the project is, we want to leave buried skeletons buried. And by that I mean, the less we disturb, the less we dig deep, the less we are bound to fix things which we don't know that existed there. So in Edinburgh, they found skeletons. When you find a skeleton, that will cost you millions, literally, right? If you don't see the skeleton, you don't know it's there, right? It's true, I promise you. And that's again what we're trying to do. So we set for ourselves quite aggressive requirements in terms of how much we want to disturb from the existing environment, because that brings with itself such obvious advantages. As I mentioned, today isn't really about the vehicle, but just to give you a snapshot, that's the vehicle. Again, the project looks at trying to extract advances in technology, mostly happening within the automotive world, and bring them over to the light rail industry. And by that, I mean two key technologies, right, which we are really exploiting. One is battery technology, and the other one is autonomous driving, autonomous control technologies. A light rail project, the light rail industry would have never had the capacity to innovate in these areas and actually drive these technologies forward on its own. But of course, billions are being put in these technologies by the automotive world, and we can carry over those technologies. Such a sized tram could never actually exist economically if you are depending on drivers. It's the reason why you see double-deck drivers driving empty all day, but we still keep buying double-decker buses, because the driver cost is such a significant aspect of OPEX that it makes much more sense, unfortunately, to pay 30% more fuel and buy buses which cost probably double when you're comparing a double to a single-deck bus. But because we fill it in rush hour, it still makes economical sense to do that way. And same thing with trams. If you look at the average occupancy of trams around the UK, you're talking about 25% if you look at the full data, right? How many seats we have on all the journeys and how many seats are we filling? 25-30%. That means we're packing trams in rush hour and they're running empty in the rest of the day. But it still makes sense to have that model because of the driver cost. I'm simplifying some aspects, right? Nothing is black and white in the world, but that is my understanding of all of it. And so if autonomy is a reality, then probably we would all agree that it makes so much more sense to have a bigger fleet of smaller vehicles, which gives you so much more flexibility with what you can do. If a small 11-meter vehicle is stopping somewhere, it's not a 30-40 meters obstacle, right? If we're designing how these trams go through our cities, if you're dealing with having to, for example, stop traffic lights for our tram to pass, one thing is allowing and accounting for 30, 40, 50 meters vehicle, and another one is dealing with an 11 meters. Vehicle safety, all of these things play into these aspects. So a smaller vehicle gives you a lot of advantages, but nobody wants them. Nobody's currently buying them because of the economics of operation of these vehicles. But we believe that if autonomy becomes a reality, then everything flips. It's the same as people believed, digital cameras can never exist until they do. And then, of course, everybody's still hanging around with reels and get left behind them. The other aspect is onboard battery. As you see, that vehicle doesn't need any catenary. It is 8-year-old technology, and with a battery the size of a Nissan Leaf, we can do 70 kilometers of running. So why on earth would you need to put catenary, right? And that's 8-year-old battery technology. We're not talking about what is available today, right? So that's the vehicle. For the project managers amongst yourselves, I thought I'll give you a snapshot of this because this project, unfortunately, it wasn't the case that we had a very rich councillor and stole, I don't know, 10 years of council tax came to us and told us, make me a tram, right? This has all been very, very hard-fought funding, which we got step by step from the DFT. And the only way we were able to achieve this amount of funding is because we had to build a lot of stage gates in our process. DFT itself did not know how to deal with our project because of the level of funding available here, right? The only way we were able to do this is we were, of course, this is our vision, but we're going to deliver this success first. If we achieve that, we'll move to the next. The only challenge with that, of course, that in itself requires a lot of work. Every stage gate requires a lot of work just to be able to pass that gate, and it of course hinders you of how you can build collaborations with especially with industry, right? People would be willing to invest, but if you only promise them the project will only exist for the next 3 months or 6 months, well, people reconsider, right? If they're gonna come along with the journey. It would have been a very, very different picture if at the very start, UK government put the money in a pot and let us use it. This project would have probably been shrunk into half the duration and probably delivered more. But it's the reality of the world we live in. We started with very, very little money back in 2017, 18. And that journey, that period was essentially going through this story, which I have been telling you. We really wanted to sort of convince ourselves that we had a strong foundation upon which to build. And then around May 2020 is where we sort of came up with the first sketches of this track, right? And we started convincing people that we could actually have something which makes sense. And then we went through a phase of quite classical system development concept to detailed to first prototype development, and I'll show you some photos of all of this process. We started filing some patents. We have 6 worldwide granted patents on the system and a few others in the pipeline. And then September 10, 2021 is when we delivered the first full-scale prototype demonstrator of the system, which convinced the DFT to really invest some significant money into the project to allow us to start building the first pilot projects. And since then, we have delivered 4 pilot projects, and I'll give you an overview of these and the reason why we had to build so many and the incremental learning we took from one to the other. So that's the first section done. We're going to look at the system now and the testing as I've been highlighting. So the first thing we did, we really wanted to make sure that there isn't any obvious solutions out there that we can actually exploit, right? Why redesign the wheel? So as you might imagine, we embarked on a journey of benchmarking. We built up FE models, cost models, carbon models, comparing basically every track configuration that we could get our hands on. The classical one, embedded sleepers, but of course slab-based track systems, built-in situ systems, top-down, bottom-up, and so on and so forth. And the sad answer was that none of the existing track configurations gave us what we needed, right? This is what a traditional track looks like, and especially the depth. And again, no project is alike, and no section of a project is alike, right? But this is what we're typically dealing with. The top bit, the last 150 for the rail and to 50 millimeters roughly underneath it with the main structural element. But then we typically need, and that blue arrow and that requirement, which comes with the vast majority of track specifications, is the biggest headache, right? They require a foundation having 120 megapascals, right, for the engineers amongst yourselves. And that property is never existing in our roads when you dig to that level, or at least you cannot assume you're going to find it, which is even worse. This is what typical that's what we might call the state of the art in track construction looks like. You have to set up a foundation, a clean foundation, which achieves that specification which I've just showed, right? And then on top of that, we typically in an urban environment are putting sleepers. Why sleepers and not slab-based like high-speed rail? Is because sleepers allow you to have continuously changing alignment. With slabs, it becomes much more challenging. You put the sleepers, you align your rail, and then we pour the main structural slab, which essentially ties in all of those sleepers together, and that we have our main track constructed. What are we doing differently on CVLR? These are different requirements. These are requirements which are quite unique to our project. No, if you would go around and ask Birmingham, Edinburgh, etc., for their track specifications, these requirements wouldn't exist. They would never have a requirement that the track system must only be 30 centimeters height. Why would you create such a constraint for yourselves, right? Unless we're, for example, in a tunnel and we cannot be higher than that because the systems won't fit. But for Coventry, that's probably one of our most important requirements. We defined that 30 centimeters to solve the issues I had been highlighting before. We did look at the rail. We did think about trying to come up with our own Coventry rail. it was just that on its own would have been a much bigger project than the funding and resource I had available. So we had to leave that alone and just use standard rail, right? Could we have come up with our unique new shape? Maybe, probably, but we just don't have the funds to deal with that size of that project. And of course, all of the logistics and supply chain issues that would come up with having your own profile, right? Which you have to roll and stock and so on. That meant, but that I had left 10 centimeters of depth to play with. So if you take 30 centimeters, you remove tolerance for real world buildability, and you remove 150 mil for your rail, you're left with 10 centimeters for your structure. Then we're putting it on an extremely weak foundation. So what do you find when you dig 30 centimeters of highway in a city? Anybody can answer that? Anything and everything. And that's the challenging bit. We could have assumed and tried to come up with a project which would suit what we might have defined 90% of the scenarios. But what good would that have been? In the reality, the designers designing a route for such a scenario would have sort of demanded, then you have to investigate all of your route. You have to make sure that you always have those minimum conditions, and then you need to start designing different spec for where you don't meet the spec, and we lose what we're trying to do here. The design process still remains actually extremely complex. We're trying to come up with something which the industry slowly builds the confidence that it essentially you could use anywhere that there is a road which is behaving well. And that means we put for ourselves a really constraining parameter there. Any highway engineers, 2.3% CBR. If at 30 centimeters you have that condition, you cannot build a road to modern specs. That's how bad that is, right? That's very soft. If you put sand on the ground and you compact it with a whacker, you exceed that parameter. We wanted to have something extremely constraining for our design, which means that we have the confidence that any existing highway we can dig up and put severe large track in it without having to do any investigation or design. The reality is people will need to get confidence with this, and we're still learning how to deal with this reality. And then when you come to the legal responsibilities of principal designers and so on, it's more difficult and complex than what I'm just simplifying here, but that's what we're trying to get to. And that's what we're hoping the industry gets the confidence of doing once we deliver a project or two, right? Because the truth is, if a highway is performing and I'm not increasing loads on it, right? And you're going to see what I'm replacing and what I'm taking out and what I'm going to be putting in terms of our track, right? Because that's the whole point of it. The reality is, but when you put those two together, so we ended up with a requirement of a slab. You can't really deliver such a project and avoid a prefabricated slab. You could be talking about casting in situ real high performance products, but that means then the manufacturing process on site is really complex. In the UK, for example, there isn't anybody that has the capability or has ever done in situ cast UHPC, right? Which would probably be needed to deliver structures at these thicknesses we're talking about here. Then there's the challenge of utilities, which we've mentioned. One thing is the utilities which are deep, right? And the other thing, but is surface utilities, so access chambers and so on. Moving these access chambers out of the way can be an extremely expensive mission. I mean, in Birmingham, there has been instances where to move one manhole a few meters away from the track, you spend £2-3 million. An access chamber, which nobody would have opened for the past 50 years. I don't make these things up. I can back all of this, which I'm telling you, I promise. But that meant that the slab that we came up had to have this ability to accommodate for this in some fashion or other, right? The other thing we sort of said, we did not want a project where every slab along a route would have a unique shape. And as we know, our cities are complex and they're old, which means we can never really travel long distances in a straight alignment. We had to come up with a system which uses a limited set of slabs. Two reasons. One, because that simplifies manufacturing, but nowadays you could argue we could come up with a smart tool in the casting process, you know, when you just, I don't know, feed it directly design, the tool adjusts itself, and we pop out uniquely slab shapes relatively efficiently. But what happens if we had to replace a slab in the future in an urgent scenario? I need to somehow precast a specific unique shaped slab and wait for it to cure and then bring it on site and use it. You see the challenge, right, with that. So that was our mission for this project, and that's why no existing system gave us that capability. This was probably one of the most fun bits of the project. We really wanted to avoid, at least I wanted to avoid, coming to a room like today and somebody telling me, "Did you think of this?" At least we wanted to make sure, right, that we did try to think of anything and everything and try to explore these ideas. And we really went everywhere. And we looked at carbon fibers, aluminum sandwich panels, 3D printing on site, and so on and so forth, right? And then we did build a very detailed decision-making matrix, which we had all stakeholders sign against before we started, so that we can value these concepts. And what we came up was this. And I'll jump through these technical slides because photos will make a lot of sense. But you could compare the existing state-of-the-art track to what we came up with. Essentially a 300 mil realistic system. And I say that because it's actually only 260 millimeters, the track itself. We left another 40 mil, which is real wear tolerance. So the slab is 100 mil, the rail is 155. And then 40 millimeters for a bedding layer. And as you see there, in the absolute perfect world, which we engineers love to work with on computers, you see where the utilities there are. They're very far from our track. In reality, of course, it's not always the case. But that's of course all to scale, and that's where utilities should be, right? Telecoms should be at 450 mil or deeper. Electricity can be at 500 mil, and gas should be at 750 mil in the highway. And so that's where the 300 mil came from, right? That's a requirement which we made up. It's something I decided on back in 2018, and it was decided to sort of give us at least a space to work in, and then give us as healthy as possible distance from where utilities shouldn't really be. We know that especially for telecoms, they can be much shallower than that. Nobody's controlling where these people are putting their utilities, and it's very common to have utilities which are shallower than that. But there are options, especially for telecoms when they're shallow. We can very easily slow and lower. That's the system that we came up with, and I think instead of trying to explain this technical drawing here, I'll explain the elements of it in the next slides. But the main elements is the main structure element is a slab, which fastens the rail to it. So we have a mechanically fastened rail beyond, of course, it being embedded in the pavement. Which sits on a bedding layer on top of whatever ground we find at 300 millimeters. That's another angle of the track. And what you see there is a section of the slab, and I put that on purpose, right? So how do you achieve a slab which is just 100 millimeters, right? I mean, we could really only achieve the requirements that we needed by using a class of concrete termed as ultra high performance concrete. Anybody has come across or used it before? There's only one nodding, and there's a reason for that. We are really behind the curve in the UK when it comes to the utilization of UHPC. Of course, UHPC isn't a brand. It's a family of products, right? And its performance can vary greatly, as you see there. Its elements are nothing special. There's nothing which is miraculous about the product. It's a cement-based concrete. We've got aggregates and filling powders. What is unique is the use of these very fine steel fibers. So if I go back to that image there, you could see those steel fibers. They're 0.2 mil in diameter. And it is what gives the flexural strength and ductility to these materials. And if you're comparing it to concrete, you could see there on that chart that we're talking about compressive strength of 150 megapascals and above, compared to your classical 30, 40, 50 megapascals of products. Yes?
You say the diamonds in 20 mil.
Yes. Needles. I've got a lot of holes in my fingers from handling them, yes. Another aspect it does use double the cement of a normal concrete, which means if you look at a ton of UHPC compared to a ton of normal concrete, well, we're probably doubling the like-for-like comparison in terms of sustainability of the product, right? It's got a lot of cement in it and it's got a lot of steel in it. But the truth is we're using a lot less of material. So even if when we compare like for like and in terms of just direct comparison in terms of net material usage, we still end up on a sustainable answer. If you start taking into account the reduction in material handling and all of the lorries involved in digging and so on and so forth, we're currently working on a full sustainability analysis of the solution, but I'm pretty confident that we'll come up with a very pleasant answer in all of this. And that's I think, one of the main conclusions out of this is that UHPC, when used in the right ways, is a magical, fascinating material. Out of this project, just out of curiosity, HS2 has actually implemented in this project UHPC. The parapet sections on the Colne Viaduct project are UHPC. It solved a massive, monstrous headache that they were having. And actually, that was a direct result of Coventry VLR. I was giving a lecture similar to this a few years back. There was one of the chief engineers responsible for that project. He discovered UHPC in that lecture. And they went and re-engineered the whole solution based on UHPC. And they were effectively able to go ahead. I would argue that the savings they've achieved on HS2 because of that project has already paid for all of the investment done by DFT on CVLR. I mentioned before that requirement we set on ourselves that we wanted to have a system that enables us that with very few slab shapes, right, we can achieve essentially an alignment. And this is how we achieve it. We have these casting channels set in our slab, which means essentially with one singular slab shape, we could achieve basically any alignment because the variation of either rotation of the slab by essentially slewing them a bit, shifting them, or cutting a section of the slab. As you see, the slab isn't symmetric, and that's on purpose. We have that end, which I call the sacrificial end. We can cut as needed at an angle to get the tight radii. So up to 80 meters radius, you can get away with the straight slab. Anywhere between 80, 100 meters radius below, we typically start cutting the slabs to get the right fitting of the rail on top of our slabs. As you could see there, that's 15 meters radius bent rail sitting on the straight slab. So as you see there, of course, the casting channel allow you the possibility to either shift your fastener and rotate it. And that's how you are able to get on just one single simple modular slab, any curved alignment of your rail. So now I've got 10 slides to show you how this happens in practice and sort of explain a bit more on the subsystems that goes. It's actually all photos taken from last summer, the majority of them, not far from here in city center of Coventry. The first stage is a classical highway process, right? Milling of our existing highways. An extremely efficient process. I think it took them about 3-4 hours to mill about 220 meters of road down to 300 millimeters. It took us then a week to deal with very, very small issues we encountered. And that was lessons learned we'll be taking forward in the next phase of the project, right? But in itself, an extremely efficient process. And in theory, if we get all our surveys right, if we know where everything is and etc., the next day, you're ready to start laying track. Yes.
What were the issues?
I will talk later. It's a detail, but for example, there was an electric cable which was completely marked. It was off, but when you're milling and you cut it, right, it was a 200 mil depth. You have to stop and investigate, and that means the process must stop. Other aspects related to design, but we can discuss in detail later. Of course, we still got a bit to do. But I think if you want a lesson learned from it, design twice and don't start digging before your design is right. Yeah. Next step. This is really just it's because we're still in an R&D phase and learning. We're taking a lot of readings and measurements on site to verify our learnings. This is what is termed as an LWD test. We're checking the bearing capacity of the ground. We're always getting much higher data than of course the 2.3% CBR as expected in such a trafficked highway. What you see up there, that's the preparation for ducting for drainage of the rails, right? So that's the only localized locations where we dig deeper than 300 mil. Well, of course, that's unavoidable to provide drainage for the rails. And down there, that's a very important detail. I've mentioned that is the ability to retain manholes within our between the rails, or hopefully shift them out, but really try to reduce as much as possible the cost of moving these manholes out of the way for no reason. Of course, if there's an access chamber, which is, for example, a telecoms chamber, which we know needs frequent access, we would never leave it between the rails, right? It doesn't make sense. But if we know it's a wastewater access chambers, we go surveying these out, and the vast majority of them are basically welded shut. They've not been opened for the last 20, 30 years. So we're saying, no, we're not going to be spending taxpayer money to move these chambers out of the way for no reason. If somebody in the future wants to come at midnight and open that chamber, guess what? The tram wouldn't be running anyways. Yeah. Next comes the slabs, just lowered into the chamber. Now, a very interesting side effect of using UHPC and having a lightweight slab is that, of course, you can manage them using small equipment. And what you see there, that 14-ton wheel digger was the only plant, besides a small dumper, that we used to build 220 meters of track. There were no heavy lift cranes and lifting equipment, just that one singular piece of kit. Which, of course, really brings a lot of efficiencies in terms of cost to site. The slab, as you see there, just gets laid on whatever foundation we find at 300 mil. There was no preparation more than just rolling the ground up, really, to just roll the disturbance that is created by the diggers and so on. Then comes the rail. We bring the rail. This is classic light rail technology. Then we bring the rail. We start aligning it, weld them. Again, just state-of-the-art solutions here with automatic heating and control of the welds and so on. But still, as always, small changes in these projects when you're innovating. As soon as you change a factor, you're creating headaches for yourselves. In this case, right? It's a completely standard process, but we still had to innovate with Pandrol, because in this case, the weld is sitting on top of a slab. Classically, it sits between sleepers. Between sleepers, there's as much space as you want. In our case, that weld is sitting on top of the slab, which meant we had really constrained in terms of the space between the rail and the slab. Hence, we had to control what is termed as the collar. So it's the extra bleed of the material around the rail. So just that small detail in itself was an R&D project we had to carry out. And there's plenty of examples of that.
They cut on site?
No. No. Essentially, we design everything beforehand, so we know the exact schedule of the slabs and how they're going to arrive. And the ones that needed to be cut, only 2 different variants. So essentially, we had 3 slab types. We get the right amount of slabs having the right shape on site. It's more efficient that way than cutting on site. That said, we did cut a slab on site. So when we worked on the alignment and we worked from both ends coming to the middle, the last slab had to be modified to fit exactly. We just took us on, cut it in 15 minutes, slot it in, and we proceed. So that's the flexibility that the project affords you. If you're bringing expensive UHPC on site and having to cut it on site and throw it away, it's not really an efficient way of dealing with things. But the ability to do it gives you a lot of flexibility. So it's a hybrid approach we were taking because it's the most cost effective. That's another first of a kind. It's another collaboration project with ACO, specifically designed for the project. Again, completely in-kind development. Most of these technologies have been developed with partners who believed in this project and have come with us on this journey. The full development and testing and certification to E600 was done by ACO. And they're receiving a lot of interest for this product because it solves a lot of headaches others have. I wanted a product which sits exactly between the rails as one integral single unit. Typically, that comes into separate sections, a middle section and the sections which go under the rail. We solved that by having. My point was that the rail is a structural element. What sits underneath it doesn't need to be structural. So we've got these shelves, water shelves that open and sit under the groove to collect the water. We open after we install the main section. Again, if anybody's interested in any specific detail, we can talk afterwards, and I can send you any detail that you want. Once we have the slabs and the rails positioned, then we bed them in place. And again, this was another innovation project. Slab bedding materials or grouts aren't anything new, but actually the product we've used here was a new development for the project. It was 8 separate ready-mix slurries of tests before we were able to come to site. We developed a product which is cost-effective enough to be utilized freely on site. So these bedding mortars are typically quite expensive products, which needs mixing equipment on site. But we said, CVLR, we have the trench available to contain the bedding material, right? So rather than going the high-speed rail way of having to shutter your slabs to contain your bedding layer and also control the flow of this, if we could come up with a product which is affordable that I can use freely, then we could avoid all of that preparation. And that's what we came up with, a product which is flowable enough to give us the functionality we need, that we can get delivered to site in a ready mix. That site consumed about almost 100 cubes of material, which we bed in a day and a half. So 220 meters, we were able to get bed in a day and a half. The next day, you could operate the tram on top of the track. That gives you an example there of how careless we can be with the preparation of the foundation. Basically, zero preparation of the foundation. That is not the case when you're putting other slabs in other systems. Typically, they try to build these perfect sand beds on which they place slabs. And if you look at Birmingham, when they're placing a section of slab track, it was quite comical seeing them lifting certain slabs up and down 3-4 times, grinding and shaving away and adjusting the foundation until you get there. In this case, just spread the slab where we need it, and then we pump the material and the material flows. Again, you can't go on site and just assume it's going to work. We had a bespoke testing site set up. We were getting the material pumping, and I can assure you the first trials, the slabs were floating and swimming away, literally. Even though we were using a material which was half the density of those slabs. We're using an aerated concrete to increase sustainability in that solution. Slab to rail interface, probably the Achilles heel of most light rail systems. It is the area which gets bombarded. This is an area of key innovation. We're actually very, very proud of this. It's looking like something very interesting. I can speak more about this afterwards. There's some details which are IP protected for the time being. But then the final stages is just building the flexible asphalt pavement around that interface, as you could see there. Now what you're seeing there, those are timestamp photos. I'm not making any of this up. March 17, we took the highway from the city. There were some enabling works before that, but that was mostly nothing to do with CVLR. The project, the Coventry City Council wanted to remove a central strip which was in this highway, and that central strip was removed from reasons nothing to do with CVLR. It had something to do with the project with the city wanting to do other projects in terms of motor fests and elements like this. So we joined the projects for cost efficiencies, and that's an element where actually we were exploiting CVLR funds which come from DFT to better the city. Rather than what some people assume we're using the city's money to do the project. Nothing could be further for the truth, even though, interestingly enough, some people actually go around the city spreading absolute lies about the project, which I find quite fascinating. Anyways, March 17, we took the road, and May 15, the tram was constructed. And actually, I'll show you something even more fascinating than just the construction of 220 meters in about 8-9 weeks, depending how you count it. And we did actually allow a lot of slack time between the processes. This was not planned and programmed and delivered F1 style. It was essentially the first time that the team building this was dealing with the system. So this was the first time Colas Rail was actually building this track. They were using the site as a training site, effectively. So we did allow a lot of slack between the different processes to make sure that delays can be absorbed in the program. Last section is almost going now a bit and back in the time and sort of explaining how did we seek to build a body of evidence to prove to people that we know what we're doing. Essentially, we follow them. Some of you might have come across a classical VM system development. That's a system developed by NASA. If you're new to it, it allows you to essentially focus your energy on where you need to, right? You break down your system into subsystems and then components and then materials, and then you test only where you need to. So if I'm using a component which is already being used, I don't test that component. But then when you're putting two components together, even though individually they might work, you're putting them together for the first time in your project, you are responsible for testing that interaction. And so that's what the project involved. And as you might see, we tested sub-assemblies, and then that gave us the confidence to go to full slab, and then the full slab was tested in lab-based in universities. And then what you see down there, for example, is what I've mentioned, the testing of the slab bedding process, fastening system certification. So of course, whenever we have standards, that's easy. You follow the standards. Actually, it's much more challenging when you don't have a standards. And believe it or not, there's no one comprehensive standard for track infrastructure. So a lot of these tests and we had to come up with ourselves and develop these test sites, right? To build confidence in the system. Yes, as you might imagine, moving from detailed design, virtual modeling, so FE modeling of both structure and vibrations have been extremely important. Manufacturing, we did even have to set up the first manufacturing of the first prototype ourselves. So what you see there, that was my COVID up there, whilst everybody was at home and the university was empty. I got special permission to build a bespoke manufacturing precasting site to cast the first prototype of slabs. If we didn't deliver those first prototypes, the project would have died. And when I started calling around the UK for people to cast for me the first full-scale prototype, basically nobody opened the door. So I bought an agricultural mixer. They used that mixer to mix animal feed, yeah? Changed its gearbox and motor and cast UHPC. And that gave us the first slabs and allowed us to proceed to the process. Process is already quite mature because these pilot projects has given us the space to learn and then implement lessons learned. And hence, even though we're still in an R&D phase, we're already quite mature in a lot of ways. So you could see there how the slab evolved from first principles to where it stands. And you could see how similar in some aspects, but quite different in others. And what you're seeing there is an evolution where we're, of course, either implementing changes to optimize for cost or implement lessons we've learned from test sites, right? And we're now very close to being to have this product as a commercial off the shelf. I'm extremely proud to say that the system has now been taken up by Vosloch, one of the world's largest railway component suppliers. And for the next pilot project, they're going to be the supplier for the system, which means this structure is going to now have the visibility of practically all of the world as they go around showcasing the systems, right? There's something quite to be proud of, I suppose, for the project. These are the 4 pilot projects we've delivered to date. The first one was just a site at university. It was just a parking, but it allowed us to really learn a lot, right? We built a replica road And then we dug it up and build a track in it, putting a lot of combinations of materials. Then we moved to putting a section of track within a depot owned by the council. It's a site where they get all of their refuse trucks coming in every day. Very important site. It gives us free loading of the track, which is fundamental when you're designing a test. The cost of running a test is usually a very significant element. In this case, loading is free. Every lorry that goes around the city, refuse truck, goes there and loads our track. And I've got an SHM system continuously collecting data. That was the third site. That was then focused on learning what the tram does to our track, right? So you could see there the evolution of requirements. The fourth one was the first time that we were able to go into a real world environment, really engage with utility owners, work through all of the processes and permits, having to work through all of the council processes, getting permits, environment and so on. Even though, of course, it's only at 120 meters, but you still have to do most of the work if it were 20 kilometers, right? Just some details on which I've said. That was the first site. Again, it gave us this ability to start learning. If we didn't have the site at university, you know, and you don't carry this, you get stuck. This site was effectively built by myself and through two lads from council's DLO, direct label order. So Coventry City Council has their own highways maintenance team. So they gave us two lads at 3CX, and we built this in a summer, making it as we go along. But it provided so much learning and so much confidence to people that came along in the next phase to help us move along. That was the second phase. You see it there before building, and that's how it gets loaded by lorries going. This has been a fascinating and very painful part of the project. We did set up a state-of-the-art, and I use the words on purpose, a high-frequency sensing setup. You would assume that if you're buying high-frequency sensors and high-frequency data loggers, that then there is also the capacity of software that allows you to visualize and analyze all of this. It's been an enormous project learning together with the project partners of how to deal with such high volumes of data and be able to make sense of it. But we've developed quite a novel system now, which is giving us really amazing data. I think I have a snapshot of some of it. That was the third site. This site allowed us to really learn what the vehicle is doing to the track. So vibration impact. So here we measured the vibration signature of the system, and of course all of the lateral loadings and so on the track. And that's we've already mentioned this. I skipped about, but there was increasing complexity in terms of the geometry that we were achieving from side to side. We started by straight, then we went a section of curved, and then we increased vertical and horizontal curvatures, right? And this was what we introduced here, super elevation as well. This is what I mentioned before. It is one thing just building a section of a track, but this shows what CVLR is able to do. We were able to go from a highway to having an operational tram in 10 weeks. That is probably a world record, even though it is just a test site, right? And that is only possible because of the complexity reduction that the project sought from the start, right? The vehicle being onboard energy and doesn't have to talk to anything on site, right? You don't have to do all of the typical testing and handshaking between all of the various systems, right? Got a 1-minute video, and then we're almost done. And that gives you an idea of the advantage of being such a small vehicle. You can bring it in on site and take it away quite efficiently. Yeah. Well, it was absolutely great.
And it was really small. Steve, and quiet.
I thought it was good, yeah. Very comfortable, very smooth.
It went quite fast, and we sat behind the driver and we saw what they were doing, didn't we? And that was really fun.
It was fantastic. It's very smooth. There's no noise.
Really liked it. It was a little bit fast at the start, but I really liked it.
Extremely impressed. Light, airy carriages, very quiet.
Very enjoyable.
It was so smooth, so quiet, so fast. You know, like it was just get people from A to B in no time. And it's, I think, it's the best thing Coventry could ever wish for. It's fantastic.
So yeah, sadly the tram had to go away, but the test site is still there and is still extremely valuable because, of course, we have another structural health monitoring system implemented in this. We've got 64 sensors embedded in that track, which is yielding us every day more and more data and evidence on the performance of that track. A lesson learned from this pilot installation, we were actually extremely surprised by the amount of positive feedback that we got. And it seems to be quite a difference between the online world, wherever there's an article about CVLR on the local newspapers, you'll get the typical, I don't know, 15, 20 comments, all of them ridiculously stupid, you know, Councillor O'Boyle putting money in his pocket, nothing could be so further from the truth, you know, or stupid comments like this. But what the people on the ground really believe was fascinating. I mean, the amount of people stopping me and asking, what's going on here? Trams? Yeah, amazing. When is it going to be ready? I was absolutely really almost like startled by it all, because what we read, with what we have been reading in the last years, you know, on the online comments, is so different from what the people in the city actually believe. So yeah, I put only this because it's one of the comments which we typically get. This is looks like a bus. Why not just put buses, right? The reality is actually there's quite a lot of evidence which comes a lot from around Europe that light rail are much more effective in creating what we call as modal shift in terms of taking people and taking them and putting them on out of a car and putting them on mass transit, right? Now, I don't believe because people really care whether it's a tram or a bus in say. I think it's the efficiencies that tram typically have and the comfort of a tram which makes people leave their cars and take trams, right? And the reliability and the confidence they have in that service. So I think if you build what is termed as a BRT, right, probably you could create similar results. The challenge is to build a proper BRT, you're practically putting the same infrastructure. It's an absolute fallacy that you can just put a bus and sort of achieve the same types of corridors without investing in building the required infrastructure. Actually, putting a bus driving autonomously on the same corridor will just destroy your highways in no time. You might have come across there's an autonomous Chinese tram-looking bus, and wherever it's been trialed, it ends up destroying the highway because asphalt and repeated loads don't go well together. As we know, so it ends up rutting the highway and destroying the highway. So if you're putting a BRT system, you have to put all of the same in infrastructure investment as CVLR would need. It's of course there are caveats in that statement, but it wouldn't be that different. Then there's of course things which I said which we don't really care about. We don't care about the pollution we're causing to this world. Not really. We just accept it, right? It's called motor normativity. The pollution that comes from cars is something we have to live with, but in reality it's killing us. But so be it, right? Because if we did value it, then we would put a lot more pressure on politicians on putting such mass transit systems, right? I'm going to run through these last slides because we're coming close to the time. That's a snapshot of what the SHM system gives us. So you see there, the line is the median response of the system, and then you see the dots is what happens when a lorry comes across on track, right? As the kind of data that we've been collecting over 3 years now at Whitley. It's probably an evidence pack that definitely no other light rail system has, and probably few structures systems have. This is just a snapshot of the studies we're doing in terms of vibration. Again, a very important element. We've got very promising results coming out of that. This last section was looking at the utilities. Utilities are probably our most important stakeholder. We've been working with them from the very start, and we've been developing a really detailed and holistic strategy of how to deal with utilities. It's a mix of technologies, techniques, and that we're putting together to make sure that we've got the tools, a toolkit that enables us to essentially leave the utilities where they are in the vast majority of instances. And yeah, I'll be presenting most of the outputs of these utilities in the annual conference of the Utility Trenchless Society in a few weeks' time. If this particular area is of interest, but we have put a lot of work in this area, and this is just meant to be a snapshot of all the work that we've been doing. What you see here, for example, is just the emergency scenario case. What if we need to remove a track? And in a case of emergency, we were able to basically remove a section of track in less than an hour. Now, this is only meant to be an absolute last scenario activity. But again, it is just to build that body of evidence. We did also, for example, demonstrate what would need to happen in the future when we're replacing rail. We've demonstrated that we have essentially what could be classed as one of the most sustainable methods of replacing rail compared to what other cities have been going through, spending tens of millions in replacing rail. We look at Sheffield and so on. And some of you might have walked this route. This is what comes next. This is the final end of this R&D program. It is a fully a full system. Will be with shared traffic. We'll have double tracks, switches, turnouts, and variants of the track delivered. And the aim is at the end of this to have a real evidence-backed specification for this novel system, which anybody can exploit, right, and use. Yes, this is the route sees a lot of environments. As I said, probably you would have walked along that route coming here from the train station. And then the vision is that hopefully we get to build the first route. But beyond the first route in Coventry, we are actually actively working and getting interest, for example, with Transport for Ireland. We are planning and developing a pilot test track there. We're also working with Transport for West Midlands, looking at putting a section of a test section there. Similarly, with Sheffield, there is a lot of interest in all of this. So hopefully we'll get there. Especially if any of you are willing to help us, we're always willing to hear for any ideas. So that was all.
Thank you very much, Dr. Nicolette. You can do it, please. I'll open the floor to questions from the audience. So will there be any questions in person? Hi, ma'am. Yep. Yes, we'll go back. And this one?
Yes, thank you. Coventry University.
Yes,
This is in the middle.
What if this is
This is the bottom.
sorry.
the list is at the bottom?
Yes, this was there.
Oh.
When are they planning on starting this? Come on. So, no, we're currently in detailed design phase, and of course working with the contractor to define how is the best way of delivering this. So we are in consultation, for example, the property owners along this road. It's a mix of residential and commercial, right? So we're looking at what is the best way of doing this, and shall we get consent to close significant sections and blitz it, or do we disturb sort of the environment for a longer period but allow much more sort of easy access to all of it? And it's of course it's a delicate balance, and we're seeing what is the best way of dealing with that. The other section is in terms of stakeholder engagement much simpler, and it gives us probably the opportunity to do longer sections of track. But this is always a fine balance of working within a complex urban environment again. But we're currently in that mix of detailed design in terms of the track and exact alignment and how to interact with that junction there in the middle. There's a series of underpasses and so on. And how to build that section of track whilst allowing access and what needs to be taken away and when. So we're still in that detail, and we're still quite a bit of weeks, probably months from having the confidence to go and start digging.
Yes, sir.
I was going to ask, what sort of adaptations are there to light rail to make it accessible to people with disabilities? Because obviously, like, so many people with disabilities rely on adaptable cars. So like it would be good to know if there's an instigation plan in place, whether they've been consulted.
Absolutely. I mean, in fact, we're working with Coventry University on that aspect. They were involved in the demonstrations we've done this summer. They were partners on that, and they did carry out surveys, and the results of that are actually going to be published. They did engage with a lot of these special requirements groups. All of that feedback has been collected, and we are of course seeing how best to build that into the project.
So I'm completely alumni. Where would I go to access these survey results?
Sorry?
Would I be able to access the survey?
Absolutely. They will be published probably free access, but if not, get in touch and share them. Yes.
Hi, yeah. You said when you milled the 300 mil off the road, you had some issues apart from striking the cable. What were the issues?
So the part of the issues is, of course, was to do with old road construction, something called when you've got stone pitch in your highway. It's something you have to be careful about, and that's something that now we've built into our processes by using specific frequency sense and GRP sensors, so that we get better idea of the road construction.
Right, stone pitching,
Yes.
that just means that it's harder for the milling machine to
No,
grind it up, or
The milling machine can't deal with stone pitching. It will
Right.
lift it up. So if you've got a layer of, let's say, 200 mil of stone pitching on your highway,
Mhm.
you can't grind away a bit of it. You have to remove all of it and then backfill with hardware essentially. It's not the end of the world really at all. It's just knowing that it's there so that you can plan for it. For example, in this case, what compounded the situation was there was a small 30 mil issue with the design process, which meant we over-milled 30 mil. And that clashed with the stone pitching. We were talking about millimeters.
Mhm.
So if we knew they were there, we would have probably sought to lift up the highway surface by a few millimeters and completely avoid the issue.
Right, and because of the low 2.3% bearing ratio, it means that you could just mill the road and then place the slabs and just pour the binder, and then that's done. You didn't have to compact the road or the ground whatsoever. Yeah.
The ground, exactly. We're talking about roads which have been there for years and years, right? So that those layers, of course, have seen plenty of compaction. And as you would have seen, we're taking a highway which is currently dealing with all highway traffic on it anyways, right? And it's there. And then we're taking out probably 150 mil of not even constructed layer, right? And 150 mil of asphalt construction of whatever composition inflation available and doing that, and putting the most advanced concrete in terms of a slab, really advanced asphalt construction on top of that. So you could see the improvement in that road construction. So of course, logically it makes sense. We've got the science and evidence and modeling to back that as well, right?
When final question, sorry. So when you have the tram loading the slab, how much of that slab area are you allowed to kind of assume is taking the load of the tram and then bearing it onto the ground? Do you understand what I'm saying?
Distribution.
Yeah, in terms of the spread of the tram through that slab, it's not 100% of that slab area is actually transmitting the tram load to the ground. Is it a proportion of the slab area?
That's the benefit of the stiffness of UHPC, right?
Yeah.
There's a really efficient stress distribution, and the rail itself, of course, is a stress distributed, right? The stress concentration doesn't directly go down. So there's a significant distribution by the rail itself. It's a steel beam.
Yeah.
The steel beam is loading that slab on multiple resilient bed locations, and so the stress is really distributed by the time you run the bedding layer. The vanish.
But you couldn't say what proportion of
I
the slab.
it in my head,
transfer
but
to
we
the-
can extract those numbers from
Yeah.
my fee very easily. I just don't have it on the head at the moment. Or I'll not say something, I'm not sure.
Yeah, one more question from the room, and then you have two online. Yeah, yes, sir. Please go ahead.
Have you any comment to make about the autonomous side of Burnley? It was suggested that they could run autonomously.
Yes.
Well, I'm just wondering, are there any tram systems actually running autonomously in the world?
Currently,
Yeah,
none.
this is what I'm trying to get at you. And is it felt they're going to be in service earlier than the severe vehicles for autonomy, or do you think?
So in terms of autonomy, right, and where we sit within the world of autonomy, right, I said none in terms of trams running autonomously on a commercial limited, but practically every tram operator is developing autonomous systems. They're talking about 2007 to 2027, 28, right? And in terms of these systems being rolled out, there are already a lot of pilot projects and autonomous. So, for example, there's in Finland, there's depots operating autonomously already. So there's plenty of pilots testing various aspects of this, and increasingly, most systems are implementing automatic seat control, automatic detection, automatic driver assist, right? So they're already quite a way along becoming fully autonomous capable. In terms of the automotive world, well, we know where the automotive world is, right? We're going to have automotive vehicles running in London this year. This is a much technically simpler problem to solve. There are autonomous buses in the UK actively running, right? There's been trials in Scotland, there's trials currently in Cambridge, and we're talking to the same partners, and we are extremely confident that this is it's not really a technical problem, it's mostly a logistical problem.
Right, moving on to a question from the online audience, from Tim Candle, retired civil engineer and RCEA member. Hello, Chris. Very impressed with what we saw in Coventry. I'm always looking forward to such innovations and how they can be applied more widely. Would this system be suitable for traditional trams? The highest loading would be the road traffic, HGVs and buses. So would the higher load of a traditional modern tram be taken by the track? And would this system be compatible with traditional overhead line electrification?
Very good question. And I didn't touch on that today, but there is a parallel program running to this. We were able to get separate pots of funding, and we are developing a parallel system. We're calling it universal track, just because of its universality to other trams. The reality is road-going vehicles have much higher axle loads, and a lot of it not even legal, but we've been measuring plenty of it on our military side, right? Where we're dealing with 13, 14, 15 ton axles, right? And also the fact that we have to design for abnormal heavy loads, so fire engines or whatever. So the slab itself, the track itself is already designed to deal with these extremely heavy axle loads. Our CVLR vehicle itself is only 5 ton axle load, and normal trams are, modern trams are 9, 10 ton axle loads, right? The heaviest Sheffield 12, 13 ton axles. And of course, it's a much more controlled loading. It's loading of the rail, and the rail itself is a distributed beam, which we can, of course, load much easier than the absolute random nature how an HGV loads our system. So it's an engineering exercise we're going through. We're extremely confident that the slab will have the flexure and capacity as the rest of the system. The fastening system itself is already certified to A+ and rating.
And also another question from online from Tim Bilby. Wait, I'll just get onto this now. Tim Bilby asks, thanks, Chris. Very interesting. Regarding life expired rail replacement, can you briefly confirm what is involved? Also, the track appears to be initially secured with adjustable fasteners. Is there any further subsequent securing in the installation process?
So yeah, fastening system. Yeah, thank you for going there. We've already carried out a demonstration of how a rail replacement could happen. It was a successful demonstration, and we've already got optimization ideas on how to make this process more efficient. As you can see there, we were able to simply cut a channel on the size of the rail, dig up that interface, that joint, that exposes our fasteners. We can untie the fasteners, lift the rail up, put the new rail down, refasten, and then reinstall the interface material. So yeah, we've already carried it out. What was the other bit of the question in terms of the fasteners?
So
the
you said
fastener system is already certified against existing standards. That's the easiest question to answer, because there are specific standards against which we were able to design and test. It's a Pandrol supplied system, which we have certified against the A+ rating. So
the question was, the track appears to be initially fastened with adjustable fasteners. Is there any subsequent securing after that?
Subsequent. So no, the rail can operate without needing any embedment. So that's what A+ fastening system certification means. We are able to potentially operate once the slabs are bedded. You could operate a tram at that point without the pavement being built around the rail, right? The rail and the other embedment will of course provide them a high degree of extra support for the rail, but it's not necessary in terms of the rail operating safely.
Thank you very much. And you had a question, sir?
Yeah. On the next test route, you mentioned about including junctions and switches.
Yes.
Does for those junctions, does the standard slab track, can you create those switches out of that, or does it require bespoke slab? Yes,
you need a bespoke slab, but we're very confident of being able to carry over the same systems, right? Those of you who might know, of course, turnout sleepers tend to have very much the same principle that we have in our slab. In fact, most of themselves are very interested in working with us to coming up with a universal slab to fit on the turnouts, which they can actually exploit for its beyond city level. As you know, there's a lot of interest in prefabricating as much as possible units before they arrive on site. So if you can send on site and the steel with a slab already assembled on it, and then you can just lower it down on site, bed it in place, and you're good to go. That's extremely effective.
Thank you very much for answering the questions, Chris. That brings an end to our presentation. As a reminder to everyone, this presentation has been recorded, and I will be uploading this to the RCEA YouTube channel very soon, after which I will ensure that we send out a newsletter to everyone who's all RCEA members, as well as people who have registered for this event, with the link to the presentation. Thank you all very much and have a good night.